Hello, fellow problem solvers. So today we're doing this amazing sequence problem. I really like the sequence problem because when I was trying to solve it, this was on an exam back when I did competitive math, and I wrote down the first 40 or 50, I believe, members of this sequence before so I could get some ideas. And that is what I'll invite you to try to do if you don't have any ideas off the bat. It's a problem I invite you to try out for a minimum of 20 minutes, ideally an hour and a half, not more than 3 hours. If on the other hand you'd like to go along with us, write out the first couple of members of the sequence, look at the problem, see what it's asking you. The magnificent ask, like this is an amazing problem, right? The sequence is just defined like this, and then it's simple enough. And then prove, wow, I'm proving something already, that for every k that's a positive integer, a natural number, the number of odd m such that am is equal to k is equal to the number of positive integers less than or equal to k and relatively prime to k. What? How do we get from this to phi of k? Wait, how did it just show up? Boom. That's why I really like this problem. Put your first couple of ideas down on paper for the next, say, 5-10 minutes. Take 10 minutes, put your first ideas out on paper. And here's the first thing for me. I look at this whole problem statement and I go, what? So when I have a what moment, what I'll try to do is write up a couple of members of the sequence. So the first couple of members are this. 1, 1, 2, 1, 3, 2, 2, 3. Yeah, and so on and so forth. Now, what you see is like for 3, you'll get, for say number 3, you'll get, okay, 1, 2, two odd numbers such that we have 3. And they were formed by adding 1 plus 2 gave us a 5, and then 2 plus 1 gave us a 7, right? And 2 we got 2 from 1 plus 1. From 1 plus 1, we got to 2. 1 was our beginning thing. And we can even have it like a 0 here would have to be, actually, how do we get a 1? We get an a0 plus a 1. A0 would have to be 0, so it doesn't really work out that well. But, so we have a 3. Then for 4, say we have a 9. And how do we get a 9? We got a 9 from 3 plus 1. 3 plus 1 gave us 1, 4, not a 9. A 9 is a 4. And then another 4 we got 15. 15 we got because it was 3 plus 1 gave us 15. And these are like the two sort of ways. These are the two 4s. Phi of 4 is like there's 1 and a 3. And we got a 1 and a 3 summed up together to get a 4. Then for 5, what do we have? For, say, 5, we have a11. We got a11 from 3 plus 2. And then another 5, a13. We got it from 2 plus 3. And then another 5, a17. We got it from 1 plus a 4. And that's about all the 5s we should get. And actually, there's one more 5 we should get, which is going to be here, 4 plus 1, a15 plus a16. So a31 will also give us a 5. Now, mind you, I believe this actually really is the problem where I wrote down about 40 or 50. Maybe even went up to 80 members of the sequence. Because the problem is just so like, wow, what's happening? Like, how are we getting these odd numbers? That is the question, right? Right? The evens like this, the odds like this. And in this sequence, is there anything you notice? Any sort of hint or idea that's sort of coming up that you think maybe could lead us to a solution or lead us somewhere interesting? So now's the time for you to pause for the next 10 to 20 minutes and try to even, push the problem further. Write more members of the sequence. See if you notice any patterns here. This is an amazingly cool number theory algebra. Number theory, what is this? Number theory because of the phi. But who cares? This is a beautiful number theory problem. I really implore you to pause right now, okay? Hope you paused. Here's the next sort of step. So mind you, how we got free? We got free as 1 plus 2 and 2 plus 1, right? We had a 1 plus 2 and a 2 plus 1. That's how we got the free. We got the 2 by a 1 plus 1. A 4 we got by a 3 plus 1 and a 1 plus 3. The order, it seems, matters here. For a 5, we got it the sums of k and 5 minus k, where k was a integer that is relatively prime to 5. So the first sort of idea, first order of business, I mean, maybe even look at, say, we have 5, 4, 5, a 7. How do we get a 7? This is a 19, a 4 plus a 3. Then if we have a 3 plus a 4, we'll have a 5 plus a 2 plus a 5, and then a 1 plus a 6 once we get a 6. How do we get a 6? We'll get a 6 from a 1 plus a 5, i.e. at a 33. Yeah, this is 5 plus 1. Yeah, that's, I think, where we get this next number. So one sort of idea is how will we get phi of k? And maybe the answer to this question is we'll get, if the numbers that are relatively prime to k are, say, I1 less than I2 less than all the way to less than I5 of k, this is equal to 1, this is equal to k minus 1, then the idea perhaps is that, mind you, this number is always even, so they come up in pairs. It's always even. I mean, is it always even? Yes. I mean, it's always even unless it's 2 or 1, then it's odd. But anything else here is even. But it says like if a is a number that's relatively prime to k, then so is k minus a. So it might be that all the pairs of relatively prime numbers that we'll get I1 and k minus I1, I2 and k minus I2. Maybe all these pairs, I phi of k. Phi of k just signifies the number of numbers relatively prime to k and less than or equal to k. I phi of k and k minus I of phi of k. Right? It might be that we get all these pairs where an is this, an plus 1 is this. Right? That is sort of what seems to be happening just right now, right here, in these small cases. No pair of numbers seems to be repeating itself, right? Can we first maybe that's one thing to prove, that no pair of numbers ever repeats itself? I mean, this would be a way for us to solve the problem. So we'd have a couple of things to do. One is show that no pair repeats. Right, so if we have a pair a and b sometime, an and an plus 1, then we will not have am and am plus 1 also equal to the pair a and b. Right, that is sort of one thing we need to show. Another thing we need to show is that all the pairs are relatively prime. Right, so we need, and if we show that all the pairs are relatively prime, then it seems to be that if we show that every single pair is relatively prime, then we need to show that all these pairs actually come up, right? So we have no pair repeats is 1, all pairs are relatively prime, and all relatively prime pairs show up. So we need to have that if k and a are relatively prime, that the pair ka and ak both show up. And if we show these three things, so if we show this thing, no pair repeats, that just means all these pairs are going to be unique, right? And if all pairs are relatively prime, that gives us that the only times we're going to have an odd number that's equal to k is an odd m such that am is k, if its sum was a sum of two relatively prime numbers, and if we show that all the relatively prime pairs show up, that means that for every k, all its relatively prime number, all the numbers that are relatively prime to it, will show up. So these are sort of the three things we need to prove. I invite you to pause for 20 minutes and see if you can prove all of these things. Mind you, the way we came up with this idea was playing around, just writing out the first 20, 40, 60, 80 pairs. I'm not competing right now. If this was an exam, I would write until I got this idea. Because if you don't have an idea for what to do in the problem, you can just, explore it by writing it out and seeing if anything sort of comes up. Maybe it's something that's in the back of your mind as you're writing down these examples, that you're saying, wait a second, how am I getting this 7? I'm getting this 7 from this. Oh, and there's uniqueness. There's no two pairs which show up again and again. And you combine these things together and you get to this idea. That's sort of the main problem-solving philosophy I want you to get from this problem, which is why I chose this problem, which is why I really, really like this problem. Because I did this. I didn't solve the problem. I didn't get all these ideas, in fact. I might have had this idea, but and I might have had the idea that this is how you're going to prove it, because how do you get 5K? It's so wild. And now this first part, how are we going to prove this? We're going to prove it, well, assume some pair repeats, and say it's the pair AB that repeats, and say there's more than one pair that repeats. And then what are we going to do? We're going to take the pair that repeats, A and B, with the smallest possible sum. Why? Why the smallest possible sum? Well, if A and B is here, then what created A and B? This sort of thing can also go backwards, right? If A is greater than B, then we had, then this must have been odd. Actually, it might not have been odd, but it feels like this. It came from A minus B and B, right? It seems like it came from this. But I want to show that this pair exists. So maybe if A was even, what would happen? If A was even, if this was even, and this was odd, then A would have come from where? A would have come from some number. So we would have A, and then B would be formed. So if this indice is 2n, and this indice is 2n plus 1, then the number, the sequence is an. So that an would have been equal to A, but that's impossible. That's impossible. It's impossible because then B would have been A plus an plus 1, which is impossible. So because B is less than A. So if B is less than A, then this is an odd index. This is an even index. And then we know that this came from, the even one came from an plus 1 was equal to B. And then an, because it's formed from B and plus A is formed from B plus an, this is A minus B. So what does this mean? It means if we have one pair of numbers, A and B, which shows up at some point, then we also can go backwards and find the pair A minus B and B. And now what does this tell us? Well, pick the pair, and mind you, if the opposite is true, if A is less than B, then the pair is, okay, let's make A is greater than B, and if the pair was BA, then we have this is going to be what? This is going to be, again, if this was even, this would be A sum 2n, A 2n minus 1, then an would be equal to A, B would be an plus an minus 1, impossibility, if B is less than A, so A is greater than B, and then we have that this index here is odd, this index is even, and we have this was a pair B and A minus B. So in both cases, we would get to a smaller pair. So if we had two pairs which were equal, right? This was AB, and then AB showed up again. We just take the pair with the smallest sum, and then this means if the pair with the smallest sum showed up twice, we could go back and get a pair A minus B and B, A minus B and B, which is another pair which shows up twice and has a smaller sum. Here the sum is A plus B, here the sum is A. What gives? Meaning there cannot be any pair unless we've gotten to a point where A is equal to B. Then we cannot really go back. But to get this part right, we just need to show that all pairs are relatively prime, because if that is true, then the only pair for which we have equality is going to be the pair 1, 1. And why the pair 1, 1 can't come up twice? Well, the only numbers which are 1 are powers of 2. Every number is a sum of 2 positive integers. After that, a sum of 2 positive integers. Yeah, it's basically every odd number is a sum of 2 positive integers. And the even number, if it's not a power of 2, it's going to be that odd number, which is a sum of 2 positive integers, right? And that's going to be greater than 2. So greater than or equal to 2, but now 1. So now we need to prove this. All pairs are relatively prime. And how do we prove this? Well, we can say the greatest common denominator behind the pairs, an and an plus 1. Or we can just say a2n and a2n plus 1. A pair is odd and an even pair. And then we can also look at the an minus 1, a2n, which is the same. And for this, the GCD of this is going to be equal to the GCD of 2an, because that's what this is equal to. And an plus 1. And here it's going to be an plus an minus 1 and an. Now we can subtract because we're looking at the GCD. And then this thing right here is equal to the GCD of an and an plus 1. And this is of an minus 1 and an. So now at the beginning, the GCD between two pairs was 1. Take the smallest pair where the GCD isn't 1. If such a pair exists, say that pair is a2n and a2n plus 1, or a2n minus 1 and a2n. And then we get to a smaller pair where the GCD is greater than 1. A contradiction because we picked the smallest pair. Mind you, this is sort of the well-ordering principle in the positive integers. You can pick a smallest positive integer in any subset of the positive integers. You can't necessarily pick the biggest one if it's an infinite set. If it's an infinite subset, you can't pick the biggest one, but the smallest one you can always pick. So this just shows the second thing. All the pairs are relatively prime. And from here it follows that if we had a pair that showed up twice, we would get to another one that's smaller and another one that's smaller, and then we would keep just doing these sorts of subtractions. But if we can't do a subtraction, that means we got to a pair AA, and that shows up twice, but the only AA pair that exists is the pair 1, 1. That only shows up once and can never show up again because ones only show up in powers of 2. Right, so this finishes up parts 1 and parts 2. And now all the relatively prime pairs show up. How are we going to prove this? I invite you here, pause for 20 minutes, try to prove this. And here's the next step. Let me clear this up. So, all the relatively prime pairs show up. How are we ever going to do this? And the answer is, there's a quote by Gauss, I think it was by Gauss, that said, I heard this was a quote, I haven't fact checked this, but a mathematician is only as good as they know how to use induction. And let's see how well we know how to use induction. I mean, the reason I want to use induction here, this is a general sort of principle. I'm being a bit funny with this, but the idea is you want to show all the relatively prime pairs show up. And the first sort of instinct is, well, can I build up And the reason I want to build up is because of the way this sort of thing is defined, right? A2n plus 1 is an plus 1, and a2n is an. It sort of makes some sense that you can use something here to have new relatively prime pairs show up. That's the idea. So let's assume, how are we going to do this? Well, induction on the biggest number in the pair. Let's assume all the pairs for all I and j that are less than k, less than or equal to k, that the pairs I and j, all the relatively prime pairs I and j less than or equal to k show up in the sequence at some point, right? This is our assumption. We've proved this for k is equal to 1. We've actually proved this for k is equal to 2. 1 and 2 to 1 show. We can even say k is equal to 3. We proved it. 3, 1, 3, 2, 2, 3, 3, 1. Yeah. That's about it. Yeah. So we've showed this for k is equal to 1, 2, and 3. Assume it's true for some k. And now we've showed that it's true for k plus 1. So for k plus 1, k plus 1 and 1, when will this show up? Well, this will show up if, so this is going to be, how do we get to k plus 1 and 1? Well, we get to k plus 1 and 1 by having previously had k and a1. If this was an, and this is an plus 1, then a2n plus 1 is going to be this, and a2n plus 2 is going to be 1. That's how we get to this one. And in general, if we have a relatively prime pair, k plus, what is this going to be? K plus 1 and t, where t is less than or equal to k. Well, how are we going to ever get this pair? Well, we're going to get it by, the previous one is going to be k plus 1 minus t. This is going to, so this is a, say an minus 1, and say an is going to be t. Then this is a2n, and this is a2n minus 1. We know this pair shows up. How do we know it's relatively prime? Well, the GCD of this is equal to the GCD of this. If this is 1, then this is 1. So we know this pair also shows up. I mean, we know this pair shows up by the inductive hypothesis because here I and j are less than or equal to k. So this pair also shows up. And this is what's absolutely amazing about this problem, right? Now, mind you, showing that all the relatively prime pairs show up in both these ways. All the pairs are relatively prime. No pair repeats. This means that the odd integers, the number of odd solutions to am is equal to k, is going to be equal to the number of relatively prime pairs which are consecutive. That's what we mean by these relatively prime pairs that add up to k, and that is equal to the number of numbers relatively prime to k and less than or equal to k. And that solves the problem. This is why, mind you, all these claims, claim 1, 2, 3, they are pretty standard-ish. Once you know some of this technique, you get to, this isn't a lot of big ideas trying to prove these claims. And this is what's beautiful about these types of problems, that you're not really asked that much, right? There's not much theory involved here. It's just, it seems scary. It seems like there's some wild mathematics that you're going to be using to prove this. But in reality, this is, once you figure out what these subclaims are, you're very well on your road to proving the thing. And this is what's amazing about the problem. And this is what's difficult. What's really difficult in competitive mathematics is figuring out what these subclaims are, right? And there aren't that many sort of general rules, heuristics that you can follow, but one sort of this meta heuristic, like this big heuristic, is to play, if you have nothing, play around with a problem like this. Another way would be to figure out how can I get 5K. Like the way, sort of the thing to motivate you to analyze pairs is because an odd number is formed by the sum of two numbers which are pairs, right? So that's why it makes some sense to look at these pairs of numbers. And you can get motivated from there, but I find it a lot harder to just get motivation from here and figure out that, in fact, no two pairs, like the fact maybe that no two pairs repeat, like when you look back at the problem, it feels like, oh yeah, this is, yeah, it's trivial. Oh yeah, this is trivial. Oh yeah, this is trivial. But it's only after you've seen the solution that all these claims seem trivial. When you're trying to solve the problem, these claims are really, really non-trivial. It's really, I mean, it's really, really hard for you to come up with these claims. And the best sort of thing is maybe, yeah, we could have looked at this and said, oh, so this means we have something, I don't know. I really don't think I generally can find solutions like this. When I was trying to solve this problem, it was literally, let me play around here. I had something in the back of my mind how the solution went, but I played here and then I realized, oh yeah, this is that problem with the pairs adding up, yada, yada. And then I have this. And then I saw, okay, how do I actually prove this thing that I think is intuitive? I knew this was just like an amazing problem, so I wanted to do it. And then I was like, okay, I need to prove this, this, and this. I would prove them. And these aren't super difficult to prove. The only thing you need to be careful about is make sure that these claims actually lead to the claim of the problem, the solution. This finishes up our lovely little problem. And as always, thanks for problem solving.